Now let's resume chapter 2. We pretty much covered 2.1 and 2.2. What is a function? We discussed it. Some terminologies like domain, range, and target, we discussed those. Examples, we had some examples including piecewise defined functions. And then the hardest aspect here was the domain part. Given an algebraic expression of a function, we have to find out a domain. In other words, we have to find out the largest possible subset of a real number in which the function expression makes sense. There are three things to remember. The denominator should not be 0. Sometimes difficult to highlight. Okay, the denominator should not be equal to 0. Inside of a radical, especially square root, should be greater than or equal to 0. And then if you have a logarithm, inside of the logarithm has to be strictly greater than 0. Now, we're not going to deal with logarithm in detail until I think chapter 4, way later. So for the time being, we're going to deal with only first two. Extremely simple cases are kind of like this. Just find out the domain, find out the denominator, set it equal to 0, find those solutions, and then expunge those out. And we have vertical asymptotes there. Another situation, if you have a radical, you'll have to solve an inequality. Inside has to be greater than or equal to 0. In this case, we have a quadratic inequality, and only between -3 and 3, this expression makes sense. Excuse me. Those are extremely simple cases. If we have more than one radical or more than one denominators, then you'll have to superpose them. That's going to be rather complicated. We'll have to discuss those kind of ramifications at the end of this chapter. In the graph part in 2.2, we talked about graphs of functions, vertical line test. Yes, vertical line test to find out whether a given curve is a graph of a function or not. Or even and odd functions, we talked about those. And then one-to-one function or not through horizontal line test. Even the one-to-one function shows up again in 2.7. We talked about it in advance in the previous video. Now let's move on to 2.4 of this notebook, which is actually entire 2.3 of our textbook. And this example, the single example, covers 2.3 of our textbook rather thoroughly, and then some. Let's find out some information from given graph, and let's answer questions. The easiest is to find out the function value. For example, how about h of 3? How do we find out? Well, after all, the graph you're looking at is y equals h of x, and in place of x, we have 3. So we have to find out appropriate point on the graph where x coordinate value is 3. We have to do the same thing, similar thing here. Instead of x, I have 5 here. So we have to find out a point on a graph whose x coordinate is 5. How do we do that? This is a visualization. h of 3 is equal to 4. How do we find out? Let me color code it as red. Let's begin with h of x is equal to 3 on the x-axis, as we can see in this red number 3, and then move vertically until you reach appropriate point on the graph where the arrow ends. And that's the point we are interested in. That's a point on the graph. And if you read the y coordinate value of that point, then that's the answer. And that's easy to see because that's a lattice point. So y coordinate value is precisely equal to 4. We can see that. How about the other example, h of 5? You cannot find out the precise value here because we do not get the lattice point there. Let me do the color coding and then resume. Okay, that's green part. We begin with x equals to 5 in the x-axis. As you can see, you have number 5 on the x-axis in color green, and then move vertically until you reach appropriate point on the graph. That's where the green arrow ends. And then y-coordinate of that point on the graph is the function value you're looking for, and it's not a lattice point, so you'll have to estimate it, about 1.7. Okay, that was easier type of problem than the next problem, which is a little bit more important. And then I always write this kind of problem in any exams whenever we deal with graphs, either in college algebra or even in intermediate algebra. I do that. In pre-calc, certainly I'll do that. I may even do something like this as well, which is actually even harder. Let's do that. Y equals h of x is given, so h of x is actually y-coordinate value. And the y-coordinate value is given as 4, so we have to find out the point on a graph whose y-coordinate value is 4. How do we do that? We have to begin from the y-coordinate this time and find out, okay, we don't need the previous graph, this is duplicated, fine. And then draw a horizontal line, as you can see here. If you do that, then what do you get? Y value is 4 in those 3 crossing points. So those x-coordinate values are x equals to 1, x equals to 3, and x equals to 8 respectively. Excuse me. So we can have multiple answers, or we may end up with no answer, as a matter of fact. If I gave you h of x is equal to 7, for example, that goes out of bound, so no, in that case, no answer. If I give you h of x is equal to, say, -1, again, no answer. When h of x is given as 0, then you're going to get one answer, because if you draw y equal to 0 or the x-axis, there is only one crossing point, and that takes place at x equals to 4. You can do things like this. Basically, what you do is find out y-coordinate value, draw a horizontal line, and then you have to get the crossing points on the graph. Their x-coordinate values correspond to the x values you're looking for. So you can solve an equation graphically like this too. Now let's go one more step. Actually, I still want this graph. How about problem C? H of x squared minus 1 is equal to 4. How do we do that? In the previous problem, when h of x is given as 4, that x value is either 1, 3, or 8. This time we have h of x squared minus 1 is given, and do we have to draw this new graph? That's going to be complicated. So what do? We use the previous result. The inside has to be, the x-coordinate have to be 1, 3, or 8 respectively. So this x squared minus 1 has to be 1, 3, or 8. Let me show you the solution here. This inside, x squared minus 1, has to be either 1, 3, or 8. So it's a continuation of the previous problem. Now, x squared minus 1 is 1, 3, or 8. We get 3 equations. X squared minus 1 is 1, or x squared minus 1 is 3, or x squared minus 1 is 8. We have 3 equations, 3 quadratic equations, and each quadratic equation will give you 2 solutions. So we have 3 solutions in the end. X squared minus 2, so we have plus or minus square root of 2. And then x squared is equal to 4, so we have plus or minus 2, excuse me. X squared is equal to 9, we are going to get plus or minus 3. If I give you something else here, again, the idea is same. And set that expression is equal to 1, 3, or 8, and then go from there. And if I give you a different number in the right hand side, then we have to start all over again actually. Start all the way from problem B. H of x is given as, say, 1 or 2 or whatever, and h of x is equal to 2 is expected to be too difficult. H of x is equal to 1, that's possible. And then whatever expression here corresponds to the x values you got in the previous part. We'll discuss more about this in composite function part, that's 2.6, and at that time you should be really ready to go toward next steps. So by that time you should feel this kind of problem feels like walk in a park. Okay, let's move on to the next problem, domain and the range. And that's easy. Domain is interval in which we have a graph on x-axis, and range is allowed y-coordinate values. And let me open up the answer key. Here it is. So, excuse me, x is changing from 0 to 8 all the way, and y is going from 0 to 5 respectively, and then I just drew this kind of light red or pink rectangle here to represent the domain and range. Okay, that was domain and range. And okay, determine the interval of increase and decrease. Again, this is pretty simple. As we move from left to right, does the y-coordinate go up or down, increase or decrease? That's a question, and it's easy to answer. And here's a visualization. In the blue part, as I move to the right, y-coordinate goes up, the function goes up. And then the red part, as I move to the right, y-coordinate drops down, and the blue part again. So we have increasing, decreasing, and increasing. And the answer should be intervals in x-coordinate from 0 to 2, 2 to 4, and 4 to 8. You never write y-coordinate in this kind of problem. Intervals of increase, decrease is all about intervals in x-axis. So this blue interval, red interval, and blue interval in the end, those are the intervals of decrease, increase, and decrease. Local extrema, okay, another trivially simple problem. A point that is higher than the other points nearby, those are local maximum, and vice versa. Points that is lower than the other points nearby is local minimum. And as you can see, we have two local minima, and those are highlighted in red, and two local maxima, which are highlighted in green. I did the color coding here. Local minimum h of x is equal to 1 at x equal to 0. Local maximum h of x is equal to 5 at x equal to 2, and so on and so forth. Okay, now let's move on to inequality. Let's see. Do you think this kind of problem was tough, B or even C? Well, still these problems are equation problems. We have equality. Inequalities are generally harder than equations, so you should be prepared. Find an interval in which h of x is greater than 4. What do I mean by that? You have to find out an interval, the x interval, where the function value is greater than 4. So function value is y-coordinates. And what do you mean by y-coordinate is greater than 4? That's what I mean. I color code it, and then the y-coordinate greater than 4, that region is highlighted in a kind of light pink region over there, not including the boundary because this is strictly greater than 4. And then the portion of the graph that goes to that region is highlighted in red. So what we have interval from 1 to 3. That's when we have this this highlighted portion. By the way, do you remember semi-inequalities are generally harder than strict inequalities? Indeed, for graphs, the same. Semi-inequalities are harder. If you use semi-inequality, you have to consider that isolated point on the right-hand side as well. And here it is. H of x is if greater than or equal to 4, then we have closed interval 1 to 3, but also we have to include x equals to 8 on the right-hand side, because this time the boundary line y equals to 4 is included. The final problem is pretty much a repetition of the inequality, and that's up to you. Okay, I don't have time to do everything, And the answer key is posted, so please take some time to do this.